Hello everyone, in this video we're going to be talking about another type of solid that usually pops up on our AP exam. Okay, so let's say we had a graph, okay? And the graph was of a circle. Okay, so let me just draw a circle. So this is a circle. And let's say the cross sections, okay, the cross sections perpendicular to the x-axis were all squares. Okay, so we're all squares. So first we have to visualize what this will look like. Okay, so I'm going to draw like a little 3D thing of it. Just remove that. I was just going to draw a bit lower. So what does it mean when the cross sections are all squares? Okay, so if this is like a side-ish view of our circle, okay, and we take the cross section, okay, that's this. And each cross section, that means if you were to chop it in half at any point, okay, then you would see a square. Okay, so this is a square. Okay, this over here is also a square. And you can see that you start to get this solid. And this is the second type of solid third type of solid that appears on the AP exam. Okay, where the solid has a known cross section. Okay, so this over here, this cross section will also be a square. Okay, and all the cross sections perpendicular to the x-axis. Okay, so like this, maybe like this. Okay, so if you were to have a region with such that this, like if you were to have a solid with a known cross section, then it's not that hard to do. Okay, this is not that hard to do. Because what is this over here? Okay, so it would be better if we use an actual function. Now that I've sort of introduced it, let's use an actual function where we can apply this. Okay, so let's have the function. Let's have the function f of x equals e to the x. For example, f of x equals e to the x, and we're going to factor in this region, R. Now, each of the cross sections perpendicular to the x-axis are semicircles. Okay, so you can have multiple types of cross sections. It doesn't have to be squares all the time. So what I'm going to do is sort of draw it the same way I drew the circle. Okay, sort of at this side/top view, okay? And each of the cross sections are semicircles. So this face will be a semicircle. This face will also be a semicircle. So will everything in between. Okay, so this is also a semicircle. Okay, and now I can start to see our solids starting to take place. Okay, and this is our solid. So what's the volume of this solid? Okay, since that's always the fundamental question. What is the volume of this solid? Now the volume of the solid, okay, so what is the volume of each of these individual cross sections? Okay, so we have a infinitely small thickness, okay, dx, okay, infinitely small thickness. Then it basically becomes like a prism, okay, like this, except that the height is infinitely tiny. Okay, so you could just use volume equals the base area times height. Okay, because it's a prism. Okay, it's a prism with negligible height. Okay, infinitely small height. So what we can write this cross-sectional area volume, the volume of a single super thin cross section, that is pi r squared over 2, since these are semicircles, times h. But h is dx. What is r? Okay, so here's what we're going to have to do. If we have each cross section over here, okay, so this is not the radius of our cross section, because look, this spans the diameter. So this red length over here, if I were to color this in red, this is a diameter of our semicircle. So we need a radius. So if this is at point x, then the red length will be f of x, right? It's kind of common logic. However, the radius will be f of x over 2. So now we should express it in terms of f of x. Okay? Since we have a dx over here, and then we can just like integrate. Okay, so we have a volume equals, well, pi times r squared. Well, r squared is f of x squared over 4 f of x squared over 4 over 2. Okay, there's another 2 here, so that'll be over 8 dx. Okay, this is for a tiny volume. Okay, so it's the differential of volume. Okay, dv. Now, if we were to integrate, okay, we can take the pi over 8 out. So you have pi over 8 is out, times the integral of e to the x squared, so that's essentially e to the 2x. And let's take the solid from 0, okay, from 0 to 2. 0 to 2, e to the 2x dx. And if you were to integrate this, you would get pi over 16. Okay, you have to introduce it to by multiplying it by 1/2 times e to the 2x. Okay, so we basically took this 1/2 that used to be over here and brought it outside, since it's a constant. So it's basically factoring. Okay, so you just take this, okay, take from 2 to 0. And what do we get? We get pi over 16 times e to the 4th minus 1. And that's the area, sorry, the volume of this solid, okay, that we just did. So the volume of this solid is exactly pi over 16 times e to the 4th minus 1. Okay, let's do another one. Okay, since they basically have a variety. So let's say we had using another easy function. So this is just like we're going to use easier functions just so we actually get introduced to how to find volumes like this, okay? So let's say we have this red region. And each cross section is an equilateral triangle. Okay, so these cross sections will be common geometric shapes, and that makes it a lot better. Okay, it makes it a lot more convenient. So each of these cross sections, okay, are equilateral triangles. So if we were to visualize this, okay, so I'm going to try my best to not. So this is our region, okay, and this is our cross section. Cross sections perpendicular to the, let's redraw this region. So the cross section's perpendicular to the x-axis, okay? They might ask you perpendicular to y-axis, but it's done in pretty much the same way, okay? Except that you have to use dy. So this is our cross section. So you have equilateral triangle. You have another equilateral triangle, gets smaller over here. So you have this solid, okay? And we want to find the volume of the solid. So what is the area of one of these tiny cross sections? The volume. The volume. Well, you could use the formula for volume of a prism, okay? Since it's essentially a prism, but with a negligible height. All right? So it's essentially a prism, but with a negligible height. So you can use this formula. So what's the base area of an equilateral triangle? So you can either derive it or memorize it. Okay, memorization is a bit better. So s squared root 3 over 4. Okay, s squared times root 3 over 4. That's the area of an equilateral triangle times the height. Now what is s? Well, s is just f of x, right? Since this is part of our equilateral triangle. So with s equaling f of x, what we can do is rewrite our volume as f of x squared times root 3 over 4 times dx. Now what is f of x? F of x is neither x squared nor 2x, okay, which are both of our lines, okay? But f of x, or the side length, is rather the distance between them. So x squared minus 2x, okay? So what we have to do is integrate the distance between them, not x squared minus 2x, 2x minus x squared. Since 2x is on the top, we have to keep it positive. So you have 2x minus x squared times root 3 over 4 dx. Now where does this intersect? Intersects at 0, and it intersects at x equals 2. Okay? So we can take the root 3 over 4 out, and what are we left with? Well, let's expand this. Okay, so we have 4x squared minus 4x cubed plus x to the 4th. Okay? dx. And now this is not that difficult to integrate. Okay, so you have root 3 over 4 times 4x cubed over 3 minus x to the 4th plus x to the 5th over 5. Okay? Now we just have to evaluate this. At 0, it will all be 0. So we only have to evaluate this at 2. So you have root 3 over 4 times 4 times 2 cubed is 8. 4 times 8 is 32. Divided by 3 is 3. 32 over 3. Minus 2 to the 4th is 16. Plus 2 to the 5th is 32 over 5. Okay, so what does this equal? Okay, so we just have to do a little simplification. Let's turn this all into terms of 15ths. Root 3 over 4 times 32, 160 over 15 plus, we're going to put this fraction over here. This is 96 over 15. Yes, 96 over 15 minus 16 times 15. Okay. 240. 240 over 15. And all we need to do is simplify this. So 160 is 96. 256 minus 240 is 16 over 15. So you have 16 over 15 root 3 over 4. And you get our total volume as 4 root 3 over 15. And we're done. We're done. We just found out the volume of this area. So no matter what the area is, what the cross sections are, you can always find the area in the same way, finding an expression for the volume of a tiny cross sections and then adding all of those volumes up to get your solid. Thanks for watching. If you have any questions, please comment below, like this video. Thanks for watching.